Welcome back everyone. In this lecture we will continue to study the isometries of R2. So as I said in the previous lecture, okay, any given isometry that can be obtained by composing two particular types of isometries. So first you take translation and then you take another isometry that is fixing the origin. So using these two types of isometries you can get any other isometry. So let us prove this. This is very important observation. So let us call it a proportion. So you start with an isometry, call it H, which is a map from R2 to R2 that preserves the distance. Okay. So this is B an isometry. So then what one can prove, there exists unique translation call it T and another isometry H naught that fixes origin. So this H naught fixes the origin such that this H can be written as T composition H naught. Okay. So this is the result and this is clear geometrically, okay, because so what you do, first you look at where this origin is mapped under the map H. Okay. So it can be mapped to somewhere. So call that point P, okay, use that point, translate back that point to origin, okay, then you can see that this translated, so once you compose with that translation, okay, or the inverse of the translation, then that will actually map origin to origin. Okay. So let us do it algebraically how it is done. So first of all, so the proof is actually kind of working backward. Okay. So if you take such maps, okay, let us say H already written as some translation composition H naught, where H naught fixes the origin. Then let us see what conditions that we get. So if you write H equal to T composition H naught, where H naught fixes the origin. So both T and H naught both are isometries, okay, that is also given, let us say. So then you can see that H of 0 must be equal to T of H naught of 0. So but H naught of 0 is 0, so that means this is exactly T of 0. Okay. So that means this T, the translation, okay, that is determined by this H of 0. So now from this you can see that H of V is nothing but T of H naught of V. So which is going to be H naught of V plus the translation. Okay, the translation usually given as follows. Okay, if you write Tx is the translation, then Tx of V is V plus x. Then you can easily see that Tx of 0 is what x. Okay, the x can be recovered from applying Tx on this origin. So that means this T of H naught of V must be H naught of V plus T of 0, okay, which is exactly H naught of V plus H of 0. So now from this you can see that H naught of V is given by, you take H of V and then subtract this H of 0. Okay. So this way you can see that both T of T and as well as H naught, they are uniquely determined by H, because T is being translation, T is uniquely determined by its value on 0. So that is already given by H of 0. So that way it is already uniquely determined by H. And now H naught of V very explicitly given by H of V minus H of 0. So that is also now uniquely determined by H. Now you can take these formulas and substitute back, then you will get what the formula for H. Okay. So now given H, what you do, given H, define H naught of V equal to H of V minus H of 0. So, it is a map from R2 to R2, no issue, and note that H naught of 0 is going to be H of 0 minus H of 0, which is going to be 0. So, that means H naught fixes the origin. Now, let us check whether H naught is actually distance preserving or not. Let us compute norm H naught of V minus H naught of W. Then you can see that this is exactly norm H of V minus H of W. So, which is going to be just norm V minus W. So, because this H naught of V is just composition of H and translation which at minus H of 0. So, it has to be actually isometric because both H and translations are isometric. So, that says that H naught is an isometry which fixes origin. So, now if you take this translation T to be the translation at H of 0, then you can see that H is given by T composition H naught, because H of V is going to be T of H naught of V, which is T of H of V minus H of 0. So, which is exactly H of V minus H of 0 plus H of 0, because T just translates by H of 0. So, then you get back H of V. So, this computation tells you that any given isometry can be obtained by composition of translation and another isometry that fixes origin. So, this means you can reduce your attention to only translations and isometries that fixes origin. Okay. So, later actually you will be studying something about semi-direct product. Okay. So, then you will see that somehow this there are these two natural subgroups of this isometries of R2. Using those two subgroups you can obtain all the isometries of R2. Okay. So, maybe I will actually tell you about it at the end of this isometries of R2 lectures. Okay. So, what we have actually observed? We have observed that any H is given by T composition H naught, where H naught is an isometry that fixes origin. So, translations are easy to understand. Okay. So, that actually reduces our problem to understanding isometries that fixes origin. So, let us try to understand them. Okay. So, if we take this isometries that fixes origin, then one can prove that they must be actually linear maps. Okay. So, let us actually give very explicit characterizations of those maps. You start with an isometry. Okay. So, let us say this is a map, just not necessarily isometric. So, then one can prove that the following are equivalent. So, what are they? The very first condition, H is an isometry such that H of 0 is 0. So, it is fixes origin. The second condition, it is an isometry that actually preserves the inner product. Okay. So, you take H of V dot H of W, then that should be equal to V dot W for all V W in R2. So, this means H preserves the inner product. So, it is a very strong condition. Okay. So, once you know that it preserves inner product, then you can prove that it is actually R linear map. Not only that, there exists unique A, which is a 2 by 2 matrix such that this A transpose is identity. So, such matrices are called orthogonal matrices. So, this is an orthogonal matrix, and this H is given by AV for all V in R2. Okay. So, we have very explicit description of this H in terms of orthogonal matrices. Okay. So, if you start with a isometry that fixes origin, then it must be coming from some orthogonal transformation, that is what it says. Okay. So, now if you put together the earlier result which says that any H is nothing but translation composition this H naught, where H naught is an isometry that fixes origin, then you can easily see that this translation you write some T W. Okay. So, I was using the capital, let us write it as capital T W. Then this H naught of V you write it as A V. Then from this you can easily see that any H which is an isometry can be written as H of V equal to A V plus W for all V in R 2. Okay. So, this is very explicit formula, algebraic formula for any given isometry. So, H of V must be A V plus W for all V in R 2, where A is some orthogonal matrix that comes from this H naught and W is this vector that comes from the translation. Okay. So, this is very explicit algebraic formula. So, we can later use this algebraic formula to conclude more about any given isometry. Okay. Okay. So, we will also see that this H actually completely determines both this capital A and W. For example, you can easily see that H of 0 is going to be W. So, this way W is uniquely determined by H. And now, what is about this capital A? This capital A is uniquely determined by this H naught. Okay. So, because that is what the theorem 1 says. So, this existence of A is unique with respect to this linear, this isometry that fixes origin. So, this A is uniquely determined by H naught and H naught is uniquely determined by H. So, that proves that both A and W they are uniquely determined by H. Okay. Now, let us get back to this theorem. This is the core part of the proof. Okay. Understanding all the isometries. So, if you start with an isometry that fixes origin, so let us see why it actually preserves inner product. So, let us just spell it out, what is the meaning of it fixes origin. So, 1 implies 2. So, H of 0 is 0 and H preserves distance. So, H of V minus H of W is same as norm V minus W for all V W in R 2. Now, since 0 is fixed by H, so by setting W equal to 0, you get that norm H of V is equal to norm V for all V in R 2. Okay. So, just work it out using these two formulas. So, what we get? We get, so norm V minus W square which is equal to the inner product V minus W dot V minus W. So, if you work it out, you can see that this is exactly V dot V minus 2 V dot W plus W dot W. Okay. V dot W same as W dot V. So, that is what you are getting. Similarly, if you work it out, what is norm H of V H of W square? So, that is again going to be H of V dot H of V minus twice H of V dot H of W plus H of W dot H of W. Okay. Now, what is this formula? Second formula says, that says if you square it on both sides, then you can see that H of V dot H of V is nothing but V dot V, and this is true for all V in R 2. Okay. Maybe I will put V dash. So, that means if you just substitute back this formula here, then what you are going to get? You are going to get, so this term, okay, let me use different color. So, this term is going to match with this term, and then this term is going to match with this term. So, they get cancelled. So, because these two are equal, then from this you see that minus 2 dot v 2 times v dot w is same as minus 2 times h of v dot h of w. So, now by cancelling you get that h of v dot h of w equal to v dot w for all v w in R2. Okay. So, that is what the condition second says. So, the condition second says H preserves the inner product. Now, let us look at this condition 2 and then conclude H is indeed R linear, and then you have a orthogonal matrix such that HV is given by AV. Okay, so, how one can get this? Since we have this condition 2, we want to prove that 2 implies 3. So, now note that this E1 and E2. So, this is the standard basis, and not only that, this is also orthonormal basis. So, what is the meaning of that? If you take EI dot EJ, then you get what is called delta Ij, canonical delta Ij. Whenever I equal to j, you get 1, whenever I not equal to j, you get 0. So, in particularly if you substitute this inside this formula, so from star you get h of EI dot h of EJ is going to be EI dot EJ, which is going to be delta Ij. So, that means if H preserves inner product, then it must map orthonormal basis to orthonormal basis. There is no other option. Okay. So, that proves that this H of E1 and H of E2. So, this again form a orthonormal basis for R2. Okay. So, now because it forms an orthonormal basis, so given any vector that can be uniquely determined by its coordinates, the coordinates are given by inner product between H of E1 and H of E2. So, now let us use this cleverly to conclude our result. Okay. So, for that what we will do, we will just compute the thing that we are interested in. So, what we need to prove? We need to prove that H is linear. So, for that purpose, let us start with u v inside R2 and then compute what happens H of u plus v. Now, note that H of u plus v dot H of w, we know that this is going to be u plus v dot w. Okay. This is again coming from star. So, this star is true for all v comma w. So, it is true even for this. So, now use this equation. Okay. So, then you can see that from this H of u plus v dot H of w is equal to u dot w plus v dot w, which is equal to, so u dot w again back to H of u dot H of w plus v dot w again H of v dot H of w. We are repeatedly using this star. Okay. Then this is exactly equal to H of u plus H of v dot H of w. Okay. So, H of u plus v dot H of w is exactly this. So, note that this formula is true for any u v w, in particularly any w. So, I can take w to be E1 and E2, okay, still the formula is true. So, then you can see that by taking w equal to E1 and E2, then you can conclude that H of u plus v dot H of E1 is same as H of u plus H of v dot H of E1. Similarly, H of u plus v dot H of E2 is same as H of u plus H of v dot H of E2. So, now once you have orthonormal basis, then we have already seen that given a vector, it is uniquely determined by its inner product with H of E1 and H of E2. Okay. So, let me just recall what we did. If you have a vector P and if you write this as x H of E1 plus y H of E2, then P dot H of E1 is going to be x and P dot H of E2 is going to be Y. So, X and Y can be recovered by taking inner product with H of E1 and H of E2. So, now you have two vectors. So, one is H of U plus V, another one is H of U plus H of V. When you take inner product with H of E1, you get the same scalar. When you take inner product with H of E2, again you get same scalar. So, that means both these vectors must be same, there is no other option. So, this tells you that H of U plus V equal to H of U plus H of V. Similarly, you can do the same kind of argument for H of C times V, where V is coming from R2 and then C is coming from R. So, then you compute what is H of C dot V, CV dot H of W. You can see that this is exactly going to be CV dot W, where C will come out. So, here we are using this inner product is linear in both variables. Okay. So, then this is going to be exactly equal to C times H of V dot H of W. Okay. So, then this is going to give you H of CV dot H of W equal to C times H of V dot H of W. And since it is true for all W's, so you take W equal to E1, E2 as before, then from that you conclude that H of CV is same as C H of V. So, these are all the two properties of this linearity. So, both are checked. So, that means this H must be R linear map. So, this is actually R linear map. Now, it is not only just R linear map, this R linear map comes from this H of E1 and H of E2. Okay. So, from that you can easily see that we have this very explicit formula. You write V as, let us say, some x comma y, then this is going to be x E1 plus y E2. Okay. With respect to the coordinate x and y, you write V equal to x E1 plus y E2. So, then if you compute what is H of V, so this is going to be x H of E1 plus y H of E2. Okay. So, now to know what is H of V, it is enough to know what is H of E1 and H of E2. So, let us compute what it is. H of E1 is, let us say, A comma B, and then H of E2 is C comma D. Now, we know that H of EI dot H of Ej is nothing but delta Ej. So, this is the orthonormality. So, that means when you take, for example, H of E1 dot H of E1, you are going to get A square plus B square. So, that is going to be 1. Then if you take H of E1 dot H of E2, which is same as H of E2 dot H of En, we get AC plus BD, which is going to be 0. Now, if you take H of E2 dot H of E2, then you get C square plus D square equal to 1. So, all this can be recorded in the matrix form. Then if you take this matrix A, whose first column is this AB and the second column is this CD, then you can see that A transpose is going to be AB CD. So, then A transpose is going to be A square plus C square So, the maybe we will compute A transpose A. So, A transpose A, it is going to be, so AB CD and then AC BD. So, it is going to be A square plus B square and then C square plus D square, and then here AC plus BD and then here again AC plus BD. So, which is going to be exactly 1 0 0 1, which is the identity matrix. Okay. So, now if you know that some 2 by 2 matrix is invertible, then the inverse must be uniquely determined. So, from this you can see that A transpose A transpose A, that must be identity. Okay. So, it is not only that H is just a linear map, this H of E1, H of E2, those vectors, they also has some very specific property. So, they are actually orthonormal, that if you spell it out, the corresponding matrix is orthogonal matrix. Okay. Now, how do you write this general H of V using them? So, then if you just work it out, you can see that H of V is equal to x H of E1 plus y H of E2. So, which is going to be exactly equal to, so because H of E1 is AB. So, that is what written here, H of E1 is AB and H of E2 is CD. So, now use that and then you can see that this is going to be x A, okay, it is x A plus y C comma x B plus y D. So, if you use matrix notation, then you can easily see that this is going to be A C B D x comma y. Okay, this is what your H of V. So, that means it is given by A B. So, A x plus C y and then B x plus d y, that is what you are A B. Okay. So, we have written this H very explicitly using this matrix A, okay, and this is true for all V, not only for just some V, it is true for all V. So, this proves that if H satisfies this condition star which says that H preserves this inner product, then H must be linear, not only that it is given by this orthogonal matrix capital A, which is obtained from H of E1 and H of E2. Place H of E1 in the first row, H of E2 in the first column and second column, then you will get this matrix capital A. So, now once you have this condition, then it is not hard to see that the defined map H from R2 to R2, which is a linear map, okay, linear map given by given by HV equal to AV. So, that must be isometric. So, how you verify this? So, you have to just compute what is norm of HV HW. So, then that is going to be exactly norm AV minus AW. So, then you can just work it out and then see this is going to be exactly norm V minus W. Okay. Why that is the case? Because A transpose is actually identity. Okay. So, if you want, let's just work it out very explicitly. A is given by A B C D. Okay. So, that is what A. Now, what is given? That A transpose is identity. So, that means A transpose is nothing but A square plus B square, C square plus D square and then AC plus BD, AC plus BD. So, this is going to be identity 1001. So, now let us just use that and then see that. So, it is enough to, so because all these numbers are non-negative numbers, it is enough to prove the square is same. Okay. But if you take the square, then what you get? AV minus AW square, it is going to be the inner product, okay, the inner product AV minus AW dot AV minus AW. Now, using this linearity, if you just work it out, this is going to be AV dot AV minus twice AV dot AW plus AW dot AW. So, this is what your formula says. So, now if you want to prove that this is same as norm V minus W square, then you need to show that AV dot AW is same as V dot W, okay, V dot W. So, this should be true for all V W in R2. So, then from this you get this equality. From this immediately you get this equality. Okay. So, how one does this? Let us again very explicitly write down, there is no issue. Okay. So, V you write it as some x 1 y 1, W write it as some x 2 y 2. So, then you can see that A V is going to be, so this is A B C D x 1 y 1. So, this is going to be A x 1 plus C y 1, B x 1 plus D y 1. Similarly, A W is going to be again A C B D x 2 y 2. So, this is going to be A x 2 plus C y 2 and then B x 2 plus D y 2. So, now if you take A V dot A W, so then what do you get? You get A x 1 plus C y 1 times A x 2 plus C y 2 plus B x 1 plus D y 1 times B x 2 plus D y 2. So, this is going to be your inner product. So, you want to say that this is same as V dot W, which is x 1 x 2 plus y 1 y 2. So, you have to collect the terms and then see what you are getting. So, for example, let us collect x 1 x 2 term in this. So, in this sum you just collect x 1 x 2 term. So, what you are going to get? You are going to get a square plus b square. So, that is going to be your x 1. So, that is it is going to come from a x 1 a x 2 and then b x 1 b x 2. So, that is going to give you this. So, now if you collect the term x 1 y 2 for example, then you can see that that is going to be a c plus b d. Okay. So, similarly, if you take other terms also you will get that. But from this matrix capital A, which is orthogonal matrix, that is telling you that this term is 1 and this term is 0. Similarly, you will get for x 2 y 1 the term 0 and similarly you get y 1 y 2 the term 1. Okay. I will leave it to you to verify. So, then that tells you that the whatever you are getting on the right side, this is same as this x 1 x 2 plus y 1, x 1 x 2 plus y 1 y 2, which is V dot W. Okay. So, this proves that the map that you are going to define using this orthogonal matrix, that is going to be isometric, there is no other option. So, now using this as we did in the earlier proof, that any given isometric map is given by composition of translation at this isometry that fixes origin. So, in particularly there exists this orthogonal matrix capital A such that H of V is given by A V plus W for some fixed W, where W is given by H of 0. So, this is the very general version of this given isometric. So, now by looking at this formula, we will actually try to determine from the various cases, so what they mean. For example, we need to get we need to say that which formula corresponds to reflection, which one corresponds to rotation and so on. Okay. So, that is something we will determine in the next class. Okay, I will stop here. So, the only remaining thing is that we have this explicit formula. Using that formula, we need to actually tell that we will be getting only the isometries that I listed in the very first class. So, those are reflections, rotations, translations and glide reflections. So, these are all the only isometries and we need to see that what corresponds to what using this formula. Okay, that I will do it in the next class. Thank you. I will stop here.